Platte River East, we went further than just the standard mesh. We put a special mesh on the end to control end zone cracking because of pre-stressing. And that worked very well. Arbor Road Bridge was a curved tub, one of the early curved bridges that we've used. And we used welded wire mesh, welded wire reinforcement for sheets that had wires in the vertical direction and wires in the horizontal direction. So we had heavy welded wire sheet used in this project. We already talked about the Herb Gray project, and the details that were used there are very similar to the Nebraska details. These are the tunnels. Also for stay-in-place deck panels, as Todd mentioned, you could use welded wire mesh, and that's a good market for you. You could use welded wire mesh in place of pre-stressing strand, because these are small products, and it can be an effective way of doing it. So that's the stay-in-place form, about 4 inches thick, with wires projecting on the outside and with some wires at the top to connect it with the cast-in-place deck. The Abu Dhabi International Airport, as I said, there was just massive amounts of welded wire reinforcement and massive amounts of beams, 2.5 meters tall, over 8 foot tall, for spans that are about 10 times, loads about 10 times the loads we use here for our bridge design. So we had to devise special welded wire reinforcement details for it. Post-tensioning anchorage zone is an excellent application for it, here and here. So the ends of a post-tensioned I-beam. And this is the tub again that we are proposing for Wekiva Bridge in Orlando, Florida, with the 2 cross wires at the top and the 3/4 inch overhang. And it comes as a sheet. The sheet is coming up here. It comes as a sheet that gets bent in the precast plant. But if you go to the slide just before that, you'll see why we wanted to have this precast stay-in-place form that covers the tub, connected to the tub, and connected to the cast-in-place slab. All of this connected together, so it's a detail that has to be done very carefully because you're converting a U shape into a box. And all of the shear and torsional forces must be taken into account. These are pictures that were provided to me by InSteel, and thank you for that, of the Bogey Creek Bridge. And here's a detail that Dyke was talking about. You could have the mesh ending at the top of the, within the tub itself, and you have U-bars connecting the tub to the deck above. So there are a couple of ways to do it. It's a massive project. I'm glad that the contractor was interested in the providing the alternate. Here we're becoming more aggressive. We're showing it as the primary option. We're not letting the contractor, waiting and letting the contractor value engineer it or revise it on a short notice. We're doing it as, for the record, as the primary detail that we want. So the cage is all assembled and lifted into place in the forms. That cage has a welded wire mesh in it, and the concrete is placed. You see the U, you see the loop bars here that project out of the top of the tub, and that's what connects it to the deck above. And that's how it looks after the forms are stripped. Very nice product. And this gives you a sense of scale. He's about 7 foot tall. One issue that I was facing as I was designing that next bridge with Kaiva, the engineer was telling me that there is no way that this welded wire mesh is going to fit in the web with uniform cover of steel to concrete to the face of concrete. And he was saying that because the concrete product is curved. And I said, Paul, it will fit exactly, precisely. No change in cover. He said, no way. I said, okay, you've got to remember that the forms are made in 5-foot segments. The forms are straight. And they are in 5-foot segments that are kinked. You don't see the kink, but that's how it's made. So if the sheet is 5 foot long and the form is 5 foot long, it's a perfect fit. These kinds of things that get people hyped up, worked up. Another thing he said, I'm not going to let you, I'm your partner here, I'm not going to let you convince me that the wires that come across the transverse wires, the anchor wires, can be overlapped and the detail can work out. Paul, the wires don't have to be overlapped. You can leave a space between them. You know, how do they develop? They have to be overlapped. I said, you don't have to develop them. They are anchor wires. They anchor the main reinforcement. This guy is in his late 40s, early 50s, and he's one of the smartest bridge design engineers I know. So there is some education that your group needs to do, and I challenge you to continue to do what you're doing. So this is the box being shipped, and I think some of it, you can see a curvature to it. That was not an error. It was not a side sweep. It's a real curvature that was built into it. This is an older picture that probably was supplied to me by Roy in the old days. Another one that was supplied by Roy. This is, I think, is a huge market for you. Precast bridge decks, cast in place bridge decks. Bridge decks, whether you do a steel girder or a concrete girder, is usually 99%, 95% of the case, is concrete. It needs reinforcement. And because of the accelerated bridge construction and the quality that welded wire reinforcement affords, you should be using it. Why is it not being used? Because perceptions exist that fatigue is a problem. It's perceptions. And you can do testing to prove that fatigue is not a problem. Railing, and this was also provided by Dyke. And would you like to say a couple of words on this?
Well, this is just an example of how you can consider various sheets and the constructability issues of bringing these sheets together and extending the reinforcing and making the foundation reinforcing also part of welded wire reinforcing. It's a huge savings for site cast in place people because they've got, they're not just, they don't have to pour the footing, they pour it in segments, but they can also plan the sheets so that you place them at the same time, and it speeds up the process very dramatically.
So this is an integration of how you plan your reinforcing in a way that includes the foundation and the wall, and have it in a systematic way that saves money and saves time as you move forward. This was slip formed, or was this slip?
Yes.
Was slip formed? Yeah.
And you know, you're looking at those foundation and some of the wires are left off because they have to be left off with a slide sheet. So those are the kinds of things you have to do as we do it. All the engineers in this organization do it.
So unless you design this carefully and you make sure that you don't have any wires in this area, this cannot be inserted down while avoiding interference with this sheet. So it has to be done in an integrated way and the whole thing done. It's just like we did with the I-beams. It takes some thinking, some planning, but it's very doable. Seating, stadium seating. Now opportunities and challenges. That's when I will hope that I don't get chased out of this room. So at least consider me your guest and be nice to me until I get done. I saw this in Spain in May. I was incredibly impressed. I knew about it. This was one of my dreams that I have never been able to realize. I knew about it, and my visit to Spain with PCI confirmed that it is very doable. What is it? It's a truss girder. It's diagonals in two planes, welded with a longitudinal bar at the top and two bars at the bottom. You set this truss girder or lattice truss in the form as they make these panels. These are partial depth panels on a bridge. So the concrete that is here is about 4 inches thick. The truss projects up another 4 inches, or maybe more or less, but about that. And they get set in place, and they have a gap in them. You can have that gap because this truss is very stiff. So you can block out the concrete here to allow the shear reinforcement of the beam to project upward. When you do this, you don't have to form for the deck. Forming the overhang of a bridge deck is one of the most tedious, time-consuming, and expensive parts of bridge building. This eliminates that. This is another detail. You see that this panel is one panel with a gap here. And with these trusses running across from end to end. And then this is all lifted up in one piece and placed in on the edge of the beam, placed here, and you're ready to pour the concrete on top. Not only that, but also you don't have to form the edge. The edge is turned up. So all you have to do is pour the concrete. I showed it to the bridge design engineer of Texas. His name is, I think, John Holt. John Holt. He said, that's what I'm looking for. Okay? So I connected him with the Spanish people. But I think he's given up. I think he did not get enough of a reception here in this country to move forward. This is something he wanted to do. And Texas is a big state. It's a huge state. And if this gets started in Texas, I am sure other states will follow. What's the problem with this? The problem with this is that if you hand weld it, then you lose economic advantage. If you machine weld it, then it is economical. Machine welding means that you have to get the machine. The machines exist in Europe, in China, in South America. They exist. And they can automatically make these trusses for you in a very cost-effective way. A second problem is that some states would require this to be epoxy-coated or galvanized. Because this is not very long, you still can do it. Or you can go to a corrosion-resistant type of reinforcement. This is the cross-section here. So you have 3 lattice girders and this width of 1.2 meters, which is 4 feet.
So, Dr. Tedros,
Yes, sir.
These steel trusses completely eliminate any deck reinforcement? That is the deck reinforcement?
They eliminate all deck reinforcement that runs transverse to traffic.
Okay.
you still have to have the shrinkage, longitudinal reinforcement, 10% shrinkage reinforcement that you can place on top of
Right on
this.
top of them.
Right on top of
Yeah.
this.
Easy. Couldn't you not place a mesh sheet on top?
You can. You can put a sheet on top that's heavy in the direction
One
of
direction.
traffic with some anchors and perpendicular to that, definitely. We even tried it in Canada,
Oh, yeah.
and we were told by the precasters they couldn't get a supplier. These are the panels being shipped that's in Madrid, Spain. And this is the bridge they have. You could tell you have the beam, then you have the deck panel running the full width with gaps in the middle. Very easy to do and very elegant. I mean, these joints are not a distraction by any way, by any means. Nonlinear stress strain modeling, that's what Dave asked me to do. So pay attention, Dave. You said, why can't we take advantage of, at least that's what I understood you to say, why can't we take advantage of the rest of the curve? Why do we have to go 80 and then flat? Or 75 or 70 and then flat? Why can't we take it all the way up, assuming that you have 4% strain? Well, yes, we can. We did that long time ago. I mean, it's back in the 70s for pre-stressing strain, and then we came up with what we call power formula. I don't think you can see it. It's right here. We came up with what we call the power formula, which is one formula that takes the stress all the way from 0 all the way to maximum. Only one formula. And with Excel spreadsheets, I don't think that it's a struggle to program this formula in. And this is the formula. And so Dave gave me the assignment, and I fitted the diagram that he gave me from ACI curves, and came up with the constants for the formula, and came up with the this diagram here. So this diagram that goes from here all the way up and then stops and then it comes down. You'd have a hard time seeing the fit with the actual diagram. So it can be done. And I think it's legal. And I think you can get another 10, 15,000 PSI added to the capacity, reducing the quantity by this much, by 15, 20%. This covers it, and thank you for not chasing me out. For listening to me.